Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
And hello, everyone. Welcome to the latest virtual classroom. My name, of course, is Francis Terezowitz. I'm an education specialist and weather observer up here on the summit of Mount Washington. You may hear a little bit of background noise with this video. We've got our night observer hard at work fixing up some observations. So if you hear any clicking in the background, no worries. We're just a fully functioning weather service, or weather station, I should say here. Today's topic I want to address is wind. And so we're going to talk about what exactly causes wind, how we measure wind, some of the variables related to wind, and then finally, why winds up here where I live most of the time are so very strong up here on Mount Washington. So without further ado, we'll continue along. So the first question, why does the wind blow? And wind is simply the movement of air from high pressure to low pressure. This little diagram here just shows just that. It shows an area of high pressure. Again, remember, high pressure, that cold, dense air with those air molecules spaced nice and close together, like tightly packed in. Low pressure, warmer air, the air particles, I should say, are less tightly spaced together. And so what happens is you get an excess of air here, and it moves to an area where there's a little bit less air. And that force there is called the pressure gradient force. And so the greater the difference between the high pressure and low pressure is, well, the stronger those winds are, the quicker the air wants to fill in the vacuum left behind in the low pressure. You can think of air a little bit like water. So when you say pour water out into a pool, the water doesn't just all stay in one part of the pool, does it? No, of course, it spreads out throughout the whole entire pool and fills it up evenly, of course. And so air is a similar thing. It's a fluid, and it's going to go from where there's more air to less air, trying to fill those gaps. And so that's pretty much how wind works. I've got some friends here with the UK Met Office. They have a quick video about wind, and so we'll take a quick couple of minutes to watch their explanation of wind. To talk about things like wind speed, wind gusts, and wind direction. So without further ado, we'll turn it over to our friends here at the Met Office.
When air moves, it's what we call wind. Although we cannot see wind, we can feel it and see it blow leaves, flags, and washing that has been hung up to dry. Winds are changeable, but some are more predictable than others. Weather forecasters try to work out where wind will blow and what weather the wind will bring. They're most interested in wind direction and wind speed. A wind vane is used to show wind direction. It is placed on top of a building or a large pole called a mast, and the wind causes it to move and point in the direction that the wind is coming from. For describing wind direction, we use compass points: north, east, south, and west. Wind direction is the direction wind is blowing from, not where it is blowing to. Therefore, if wind comes from the east, we call it an easterly wind. At an airport, you may see wind socks. They are also used to show wind direction, but they show where the wind is moving to. It is also useful to know wind speed. To measure this, we use an instrument called an anemometer, which looks like this. The faster the wind, the more quickly the cups on the anemometer spin around. It is important to know the speed of the wind. The faster it is, the more damage it can do. We have different words to describe how fast a wind is blowing. A gust is a sudden rush of wind which can catch you by surprise. A gale is a very powerful wind. It can be hard to stand up in a gale. and it's best to stay indoors.
All right, so that was a brief introductory video about wind. And so now we're going to change gears and talk about why wind up here on Mount Washington is so strong. And I skipped ahead. Oh, no, I did not skip ahead. I thought I skipped ahead on that slide. So it's a combination of factors, including our location in the United States, our topography or the terrain you could think of, the frequency of storms, storms like those big nor'easters, those mid-latitude cyclones we talked about a little bit with the air masses unit. And then finally, the Venturi effect, which I'll talk a lot more about in just a couple of slides. And so first, it's all about location. Mount Washington, we're located here on the northern part of New Hampshire. We're the tallest mountain for about 1,000 miles. You have to go all the way to South Dakota for our peak that's as tall, and then to our south, you have to go all the way down to Mount Mitchell. It's a little bit taller than us down there in North Carolina. But what I want to bring your attention to are these prevailing winds. These are winds that are the most common direction for winds to come from. Typically west to east. That's sort of the name of the game in the northern hemisphere. At our latitude here in the United States, and so there's nothing really to slow those winds down for 1,000 miles. So they get plenty of time to accelerate and hit us with their full force. So those winds get to us here on the summit. Here we go. Winds get to us, and they meet up with the terrain, the local topography that we mentioned. And so you'll notice that they come in sort of a triangular fashion. That's because the actual White Mountains and the presidential range itself is shaped a bit like a triangle. And so those winds start with a much wider area and then get squeezed together by that terrain. And so that causes them to accelerate a little further. I mentioned storm tracks. That little white star there is us here on the summit. And each of these red lines is a common storm track over the last 30 or so years. The thicker these lines are, the more common the storm tracks are. And so you'll notice there's a cluster of storm tracks that are very, very close to the summit, within about 1,000 miles or so. Some of these thicker lines are these common coastal storms that we call nor'easters, which we'll be talking about actually in a future virtual classroom, so stay tuned for that. And so with all these storms traveling again, west to east along the jet stream, those prevailing winds, it pushes all those storms over us. And we've got multiple jet streams sort of converging in the general area of Mount Washington. And so whether they're to our north or well to our south, the storms can have some sort of impact up here on the summit. Speaking of storms and more of the meteorological reasons for the strong winds up here, I want to talk a little bit about the tropopause. And what the tropopause is sort of the lid on top of the troposphere. The troposphere is where, well, our weather occurs. And so with this lid, you can't really have winds mixed above this. And so what happens is, especially during the wintertime, this tropopause is a lot lower because the air is colder, it's a lot more dense. So the top of that troposphere is lower above the summit of Mount Washington. And so the winds obviously can't just go right through the mountains. They're forced up and over underneath that troposphere, or tropopause, I should say. And what we get is a squeezing of the wind. It's sort of like putting your thumb on a garden hose when you want to reach, say, a flower that's further away from you or whatever. You're putting your thumb on that water, you're restricting its movement, and so it's increasing its velocity as it's coming out of that hose. And so the similar process occurs here on the summit. At the base, we may see winds only around 25 miles per hour. Still a pretty breezy day. You might lose your hat. The trees will definitely sway, but up here on the summit, we're talking about hurricane force winds. And in the wintertime, we can expect winds around 100 miles per hour every 4 days or so. Speaking of strong winds, in April 12th, 1934, we had a 231 mile per hour sustained wind recorded up here on the summit. This holds the record for the world's highest wind speed observed by people. And so we had 4 observers starting off the observatory in a much smaller building than I'm in right now, much smaller than the Sherman Adams building. I can only imagine the sounds that they heard in that building with just the chains holding the building down. And so it was an incredible day. They used an old-fashioned anemometer. And so I want to now talk a little bit about anemometers. This is our RM Young. And you'll notice this propeller on the front of it. And simply, the stronger the wind is, the faster this propeller is going to move, of course. And you'll notice as well this nice big fin on the RM Young. This will actually adjust the direction of the RM Young and give us a sense of which way the wind is blowing from. Again, remember, we're measuring the wind coming towards us, not necessarily the way it's going. And so this will actually point into the wind with that big old fin on the back. Speaking of fins, this isn't the only instrument we have up here. It's made out of plastic, and so plastic is great in the summertime. This is actually better in lower wind speeds. When we start getting that thick rime ice building up, we want to keep instruments safe and without getting damaged. And so the RM Young is not too good and not being damaged. And so during the wintertime, we'll take the arm young down and we'll transition over to the pitot anemometer. I talked a little bit about the pitot tube a few lessons ago, but we'll just do a quick little review here. I'll come right up to the camera. The pitot tube essentially allows wind to come into the front of it. It's got these little holes on the side that you can probably just barely see under my finger. And so the difference between the force of the wind blowing into it and the air pressure along these four little holes gives us a sense of the wind speed. Of course, there's electronic instruments that this pitot tube is attached to. But you'll notice this pitot tube also has a fin, so it can also point it to the wind and change its direction based on which way the wind is blowing. But the cool thing about this is that we can heat it, and so it won't freeze up or get damaged during those really strong and cold wind events during the wintertime. We display the data from the pitot tubes on our haze chart, and a haze chart is simply a piece of paper that gradually rotates throughout the day. And so it's attached to the pitot tube above my head. And so the stronger the winds are, the further out this red line is going to go. And pitot tube is attached to this little arm here. The arm has a little bit of ink on it. And so we'll notice it moving around all day long as that circle slowly rotates throughout the day. And so just a quick example here, we'll pull it up on the full screen. The haze chart you see there is our strongest wind in the 2000s, February 26, 2019. The maximum wind gust was 171 miles per hour, actually going off the chart there briefly. So quite an incredibly windy day. Behind me, the haze chart's a lot less busy. I would show you, but it's really not all that exciting. It's just pretty much a concentric circle around the middle. We've also upgraded our pitot tubes. So this is our newest pitot tube. This is the next generation. This is able to measure winds up to about 300 plus miles per hour. So an incredible piece of equipment here. And what you're looking at here is just a cross section. We've got those two sensors detecting the difference in pressure. Pressure, of course, going in versus the pressure around the tube itself. So again, that greater that difference in pressure, well, the stronger the winds are according to the sensors. So I've got a few quick videos to show you guys just of the winds up here on the summit of Mount Washington. The first video here is 131 mile per hour gusts. What you're going to notice is a piece of metal there, wind vane actually, moving in the wind. So basically what I'm going to do now is just be quiet and allow you to hear the force of those winds. Just briefly, we'll move on to another quick video as well. So we'll go full screen here, and I'll just hit play, and welcome to the world's most extreme weather. And so I just wanted to give you a sense of some of the strong winds that we've experienced up here on the summit. Again, this isn't even close to the strongest gusts that we've experienced, but still quite dangerous to be outside in that. You know, and when winds are associated with precipitation, especially precipitation below freezing, we get all sorts of icing here on our equipment. This is way above my head, about 60 feet above me in our parapet tower. You'll notice our two pitot tubes standing tall. Our RM Young is nowhere to be seen because we've taken it down at that point. But you'll notice these are not covered in ice compared to the rest. We've got about a foot thick glaze of ice on just about everything, every other surface on the summit except for these two pieces of equipment. We're able to heat those up to about 80 degrees, even during the strongest and most fierce storms up here on the summit. And so we're able to continuously collect that wind data to submit to the National Weather Service and to further prove that we are indeed home of the world's worst weather. Winds also do occur during the wintertime, so we're going to step back outside. That event that I mentioned back in 2019, the February 25th event with 171 mile per hour wind, well, this is what it looked and sounded like. You'll notice, again, all the anemometer is working. And you also notice in this one a lot more rime ice as we are well below freezing in this video. So without further ado, let's step back outside into the parapet ring, and here we go. Skip ahead just a little bit. All right, we'll pause it out there. We don't want to get too cold in those strong winds, of course, but you'll notice we had our observer de-icing the instruments with a long metal pole, or sometimes we use a mallet. But in this case, the winds were a little too strong for their comfort to even go up into that uppermost part of the parapet. So they stayed down and just sort of whacked at the ice. Our saying up here is less ice, not ice less, especially if it's really dangerous like those conditions there. Oops. Skipped ahead to the end of the slide here. We'll navigate back. I want to end here with some main takeaways. First, wind is the result of the movement of air from high to low pressure, that pressure gradient force that we talked about. Mount Washington up here sees such strong winds due to its location on the east coast of the United States, its topography, its prominence above the rest of the land, as well as the surrounding mountains acting a bit like a funnel for those winds, as well as the Venturi effect. Again, remember the top of the troposphere being lower between the top of the mountain and itself, and so winds being squeezed between those two sort of walls, if you want to think of it that way. And finally, the frequency of storms, so the amount of storms that are around Mount Washington in a given year. Our highest wind speed, of course, 231 miles per hour, still the world record wind reported by man. And finally, we use those anemometers to report wind. A wide variety of anemometers up here on the summit. We're actually the only observatory that uses those pitot tubes to record wind. Just a fun fact for you. And so we will go now to the final slide. This is just a link to our website, mountwashington.org/classroom. You can find all of our earlier virtual classrooms on that website. You can also submit questions and answers for our live Q&A session, of course, held every Tuesday at 11:15 a.m. Eastern Time. You can submit your questions by registering through Zoom or going to my email, fjarazowitz@mountwashington.org or education@mountwashington.org. So I want to end the presentation just by going to mountwashington.org/classroom. You'll navigate the site here. There's plenty of information about our past programs you can find. You can also find information about further resources, as well as links to our previous lessons, as I mentioned, and our live Q&A. So without further ado, I'd like to thank you all for joining me today, and I hope you learned something a little bit of something about the wind. We'll see you for the live Q&A in just a short week. Thanks again for stopping by.